Hello there, my name is Anand and welcome to the third video of the Program Your Robot series. In this video, I'll be demonstrating how to use Phoenix Tuner to tune a simple PID loop using a Talon and a versaplanetary integrated encoder. I've got an arm here on a 90-to-1 reduction with my versaplanetary encoder on the output stage, and I'll be using a PID loop to make it go to a position. If you're watching this and don't know what PID is, check out the link in the description to find a great video that shows how PID works and why it's useful. Now before I begin, make sure you're on the latest version of the tuner and the Phoenix library, otherwise you risk it not working. Also make sure that you use the Install Phoenix Library/Diagnostics button to install all the stuff on the Rio. Note that the tuner does not allow you to control devices over Ethernet, only over Wi-Fi or USB, so make sure that you're not tethering using Ethernet. Now, that's only at the time of making this video. They may have added that feature since then, but for this video I'll just be using Wi-Fi to connect to the robot. So let's get started. First, I'm going to go and change my network to my testing board Wi-Fi. And there it is. Joystick's not plugged in right now, so I'm getting a small warning, and that's okay. Sometimes we get those. Now, I'm going to go ahead and make sure that my IP address is correct. So I'm going to come over here to this guy here, the second tab, and it tells me my robot IP address is going to be 10.10.72.2, so let me change that. 10.10.72.2. And I've already got Phoenix Tuner open here. If you don't have it open yet, do that. I'm going to hit Install Phoenix Library/Diagnostics. And it will install the Phoenix Library or Phoenix Tuner stuff onto your Rio. Now, you don't have to do this if you've already done this once. But I'm just making sure that because I changed from USB to Wi-Fi here, that I reinstall it just to be safe. Okay. Now Phoenix Tuner has a few different tabs, as we know. We've got a CAN devices tab that shows us what we have on the CAN bus. So in this case, I've got my Talon and my Victor. I'm going to select my Talon. CAN IDs, blinking it to change to get rid of the sticky faults, all sorts of things. There's the control tab, and that's really what we're going to be using today mostly. We've got our config tab here that lets us configure all of the different settings of the Talon and Victor. Self-test, that tests itself out. And a plot that will plot all of the stuff for us. So we're going to start by using the control tab here, and the plot tab here to make sure that we get started. All right, so first thing I'm going to do is I'm going to go ahead and reorganize this because it's kind of hard to look at here. So first I'm going to drag my control tab right onto the left side here. And I'm going to drag config also to the left side like that. And I'm going to squeeze in config because that really doesn't need to be that big. I'm going to make control a little bit larger so I can see my set output stuff here. And I want to make sure I can still see the plot, so I'm just barely leaving enough space here so I can read the descriptions and stuff and see as much plot as possible. Before we get started, let me go ahead and show you my code here. So the code is really straightforward. Everything else is just the old stuff that we had from video 2, plus a zero test encoders thing that just zeros my encoders. But basically all I'm doing is, in my controller init, I'm doing config factory default, setting the neutral mode to brake mode. This doesn't really affect closed loop control. Configure my feedback sensor as a CTRE mag encoder relative. That's the same as the versaplanetary encoder. I'm going to set my selected sensor position to 0, so I'm going to 0 my encoder when I upload this code. I'm going to set my inversion, and I'm going to set my Victor to follow my Talon, even though my Victor is not connected to anything right now. With that out of the way, let's get started. So you'll see here that my plot, I just uploaded the code there. You can see I've zeroed my encoder now. So my sensor position is at 0 there. And so first thing I want to do is I'm going to make sure that my position increases positively with positive output. So I'm going to go ahead and change my set output stuff here. So I'm going to drag this over so you can see a bit better. So you see I have this little slider here that lets me control with the slider. I don't really want to use the slider control because I accidentally slide it too far and go to 100%. So I'm going to first just use these little boxes here. So just say 0.1 and negative 0.1. Pretty conservative outputs there, 10%. And resize this window so I can see this nicely. All right. And with that out of the way, I'm going to enable the robot. There it is. And I'm going to enable control here. And now if I set my output, there you go, positive output is causing positive position change. You can see it kind of levels off there because it doesn't have enough power to go any further than that. If I do negative output, goes the other direction. And again, settles because it doesn't have any power to go any further than that. So I'm going to go ahead and set 0 here, stop it from moving. And now I confirm my sensors in the correct direction. Positive output's going to make positive sensor position change. And that's what you want when you're doing any kind of closed loop control. And you can change this by using the set sensor phase in code. I didn't do that because I was lucky and it just worked out. But you should be using set sensor phase or to make sure that your sensor and your motor output are in phase, that they both increase positively with each other. Now next, let's go ahead and get started with the PID. So I'm going to enable my plot again. And I'm going to change my control mode. I'm going to disable my control first. Change my control mode from percent output to position. And I want to set my target positions as being some fraction of a whole here. So we've got a calculator here. For a CTRE mag encoder or a verse planetary integrated encoder, 4,096 ticks will be one full rotation. Now for this arm here, I only want to go maybe to like plus or minus 90 degrees. So 90 degrees divided by 60, that's going to be a quarter of a circle. Then I'm going to multiply that by the number of ticks per rotation, and that's 90 degrees, 1,024. So I'm going to set my targets as being, for now, 600 and negative 600, slightly less than 90, just so that I can first tune my PID loop with a small oscillation and then move on to a larger one. You know what, I'm going to start my output at 1024, 0 to 90 degrees, just to be a little more realistic. That's really what we want our arm to in real life, so I'm going to go ahead and set it 1024. So now let's start tuning our PID constants. So over here is slot 0, and you can see we're using PID slot 0, and slot 0 on the Talon is going to store a set of PID constants along with some other terms. Now we've got 4 slots we can use, so we can do like a position PID, a velocity PID, etc. Today we're just going to do position PID because that's really the most useful of the few when you're controlling the arm. So first thing I'm going to do is start my KPI with something small. So again, I'm going to use my calculator, and I basically want, when I have, say, 1024 error, right? So I'm at position 0 and I want to go to 1024, I basically want to have 100% output. Why is 100%? Because I'm scared. This thing's mounted to a chair right now, so probably not 100% output, let's say like 20% output. So I'm going to multiply this by 0.2. But I divide that by that, and I get a peak constant of 0.2. Just taking my error, dividing it by my peak output, or the output that I want, and I get 0.2. So, with that in mind, let's change my KP to 0.2. Go ahead and hit save there, and let's go ahead and enable the robot and try this out. Alrighty, so let's go to driver station. We're enabled here. Let's go ahead and set our value to 0 first, come at 0. Enable control. Let's go to 1024. And there we go. We can see that we're getting a fair amount of output there. Now we're not quite getting to 1024. We're only getting to about 450 there. So my KP is probably looking a little weak. So I'm going to just double this here. Let's hit save. And typically for your KP, if you're not sure where to start it off at like 0.01. Starting off at 0.2 is a little bit aggressive, and if you're off by like a factor of 10, you wouldn't be so well. If you're off by a factor of 10 on a 0.01, you'd probably still be okay. In any case, I've saved this. Let's re-enable control here. All right, getting a bit better, up to 700 now. Double it again, up to 0.8. Hit save. And enable control. And there you go. We're actually starting to get to the position now. You see how we overshoot a little bit and then come back? That's pretty good. Now, it's going a little fast for my liking, especially because the stool it's mounted on isn't very rigidly mounted. So I'm going to go ahead and slow down this output just a little bit to try and curb its acceleration. The first thing I'm going to do is I'm going to set my closed loop ramp up here. So this is the number of seconds from neutral to full. So I'm going to start this off at maybe like 0.4 seconds to go from a 0 to 100% output. Hit save. Set to 0, enable. You can see that sounds much cleaner. It's actually doing a proper ramp now. Pretty good. That's looking pretty good. I'm going to set this a little bit smaller just so I can leave a bit more for my PID here. but looks like it's in a pretty good spot. And it's not likely to tip over the stool anytime soon. So KP is looking pretty good. I guess I could increase a little bit more here. Where's my KP? Here you go, KP. Let's make it 1.0. And then you notice I'm increasing it by less and less as time goes on, just so I can be a little bit safe here. Enable control. And yeah, it's looking pretty good. It gets to the position almost. There's a little bit of steady state error there, about 50 units, but it's not terrible. Now what I want to know is how do I curve this output? Because I don't want it to like swing around like that, right? So yeah, we're at about 40 units of error. So how do I decrease that swing there? And the first way you're going to do is you're going to start by tuning your KD. And for most systems, you want to only start tuning KD after your system starts oscillating about the set point, like going back and forth, back and forth. But in my case, because I have this very heavy arm on this pretty small reduction, it's not really going to start oscillating until things get violent. And if things get violent in my bedroom, then bad things will happen to me. So I'm going to start tuning KD now in order to demonstrate how it dampens the output. So let's start KD off at a value that's, say, 10 times KP. Let's start that off at 10. Save. Go to 0. All right, didn't seem to do much there. So I'm going to go ahead and triple it up to 30. Save it again. Go to 0. Much better. You see that how the overshoot is much decreased now? We're almost have no overshoot at all. That's beautiful. You also notice if we get a little bit jerky there, adding too much KD will start jerking around your system a bit. Now, in this case, it seems to be doing okay though. The jerk might have just been like a small comms error or something. So this is pretty good. Typically, if your KD goes above 100, then you'll start getting funky errors. All right, so now that we've got KP and KD reasonably well tuned, so I tuned KP until it oscillated, or started overshooting a lot, and then I increased KD starting at 10 times KP until I saw less oscillation and less overshoot, which is good. But now I'm still getting steady state error on the order of about 80 units now. That's not great. Now how can we reduce steady state error? Well, that's what KI is for. So I'm going to start KI off at a value that's 1,000th of KP, so 0.001. In fact, I might even start off even smaller at 0.0005, just to be safe. KI can induce really big oscillations if you're not careful, and so I am always careful when it comes to KI. KI is the stuff nightmares are made of, but it also does fix a steady state error by increasing your output until you get to the set point over time. So I've done this, let's hit save. Go to 0, enable control. Let's go to 1024. And I've got my hand over the enter button to disable things go horribly south. Better. You can see the overshoot there increased a little bit, but now you'll notice I no longer have much steady state error. The integral term's already doing work, even as tiny as it is. You'll notice we still do dip down underneath a bit because my KI is pretty weak, but it's doing pretty good so far. So I'm just going to double KI up to 0.001, hit save, and enable control. And you'll notice now that my overshoot is actually pretty significant. It went from almost 0 units to about 1,200. And that's not great. If I want to reduce my steady state error without making my KI term make this thing go out of control, then I'm going to have to use what's called an I zone. So the I zone is basically a thing that says if my error is larger than this number, don't add anything to the integral term. And the reason for that is that when I'm very far away from the set point, so I'm going to go to 0 here. When I'm very far away from the set point, the integral term thinks, oh, I got to add a lot to my integral accumulator now. So basically it just builds up more and more integral until it hits the set point. And unlike KP, which is 0 when it hits the set point, KI is going to still have this big integral accumulator, so it's going to overshoot, and then it's going to subtract from the integral accumulator, and then it's going to finally, slowly come back to our set point. Not really ideal. So I want to add an integral zone, or an I zone, to basically tell it, stop increasing output. Okay, so let's start this off at a value of maybe 200, or 150. You'll remember that my steady state error before was about 80 ticks, so if I start using my integral 150 ticks away, then it should be pretty good at stopping it from undershooting, but also stopping it from oscillating a lot. Let's save this, set value to 0, enable my plot, enable my control, and let's go. Much better. You'll notice that my overshoot there has decreased. I'm still getting a little bit of oscillation for integral, but it's doing a pretty good job staying on the set point. And in FRC, you don't really need your arm to be in the perfect spot all the time. Some people do, but for the most part you don't. So right here, we're already starting to get fairly good results. Some of this oscillation is because I'm getting some comms errors here. Yeah, so you've already gotten 7 there, 8 now. But this is pretty good. Oscillates maybe like 10, 20 ticks around a set point. Alright, so let's go ahead and finish tuning this thing. So right now I've got my thing going to a position. It's still a little jerky. It's still not doing quite what I want. My integral term, to me, it seems just a little bit too strong for me to feel safe. So first thing I'm going to do is I'm going to keep my Ki here, but I'm going to increase my Kp so I get closer to my set point without relying on the integral. So I'm going to make this like 1.3. I'm going to reduce Ki a little bit just so it doesn't have as much of an effect. Typically changing 2 variables at once is a bad thing, but in this case I'm reducing a variable and increasing a different one, so it's probably okay. Let's save this thing. Enable control. Oops, there's my plot. Oh, we just missed it. And so I'm doing a pretty good job. It's doing less integral oscillation because I've reduced my integral, but it has a bit more overshoot because of the Kp. So I'm going to start by doubling my Kd to 60. Oops, right there, 60. Save it. Go to 0. Enable. And that's pretty good. And see now my overshoot is greatly decreased. And actually at this point I'm feeling pretty good. It's still a little shaky. But part of that is because you'll notice that my output is jumping suddenly quite a bit. Part of that is because of the neutral deadband here of 4%, but mostly just because my gravity compensation isn't quite there. And so it's not very good at figuring out exactly when to stop. But for the most part, this is pretty good. If I wanted to say like score a ball or something with this kind of accuracy, I'd probably have pretty good odds. And the other thing is, my gear ratio is very small, my mechanism is quite large, and that's going to cause some errors. The bigger your gear ratio is, the more controllable things are going to get. Still got a little bit of overshoot there, so let's increase Kd from 60 to 90. Save that. Better. You'll notice now that we're undershooting the set point, we're not quite reaching it, we're relying on the integral to get us up there. So I'm going to increase Kp again, up to 1.5. Save it. Enable it. The overshoot is back, and integral is still kind of doing its weirdo thing. Let's go ahead and try reducing the integral and see if that fixes our problem. Because right now I'm getting a lot of integral wind up back and forth, and I don't really like that. So I'm going to about halve my integral here. 0, enable control, and there you go. Now Phoenix Tuner makes this very easy. This process of tuning and tweaking parameters is really easy with Phoenix Tuner. Doing this in code or making your own thing to do it is possible, but doing it this way lets me see all the different settings I can modify to make this work. At this point I'm feeling pretty good with this PID loop, so I think I'll end the video here. The next video is going to cover the code for this example and how to pour all these constants that I've set up into my code. Very straightforward, actually. And the video after that's going to go over a better control scheme called Motion Magic. And Motion Magic is going to take a lot of the problems we've seen here with the jerky motion and not approaching set point properly, and it's going to solve them by using what's called a motion profile. Well, thanks for watching, and I'll see you again soon.